So in the first part of the radio subsystem, we take care about the radiation and the reception. We think about the antennas which we need actually to couple our wire, where we usually transmit our data, into the air. The air is our medium where we can vary frequency, where we have the space, where we have the time, and where we have the code also for other technologies. And now we think about this coupling part, the antenna, with which the electromagnetic waves are transmitted into the air. And therefore, our theoretical model is the isotropic radiator. The isotropic radiator means that we have a certain point which symbolizes our antenna. And from this antenna, actually, there happens an omnidirectional radiation. So that means the radiation is equal in each of the three dimensions, x, y, and z. And this actually forms a sphere in which the radiation is emitted. Actually, in reality, there are some differences. The emission is not like in a sphere in this isotropic radiator model. It rather varies much more depending on the surrounding objects. And this finally leads to fading over time and space, which then happens in the communication between the mobile station and the antenna and the fixed antenna. If we look into real antennas, then we see that there are mainly other shapes than this isotropic radiator. For example, this square, which you can see here on the right side, square-shaped antenna, which in the side view like this plane here. And if you use this plane for the emission of electromagnetic waves, then it forms a coil like this one here, so that it's emitted in a certain direction with a certain power distribution in the air. And then the model in this case would be that inside this coil you have a certain power level which you can receive, and outside you cannot receive anymore, and you're not able to communicate to this antenna. And then you can use these kind of real antennas, these planar antennas, for building sectorized antennas like we have in the GSM system. In the GSM system, we have antenna buildings, actually, where we see that there's some pole on the roof, for example. And on this pole, there are sometimes emitting several antennas in different directions. And therefore, we take multiple antennas and direct them with 120 degrees difference in this circle here to form such a sectorized coverage of our area. And therewith we can get such a sectorization of our area, and these circles here symbolize the radiation which starts on such a planar antenna directed into a certain direction within this area. What we actually do here is that we introduce an additional space division. So in the later slides, we will see that we use space division as one multiple access scheme to get more users in the area. And here, the sectorization leads to even more space division. Not only an antenna here in the center emits in all directions, but there are three different antennas, three different planar antennas, which sectorize the covered area. Now, actually working with these circles is the ideal world. What we have in reality is that we have some planar antenna, and then there's a coil forming maybe like that here, so that we have a certain radiation, and this radiation is maybe also asymmetrical. Like here, you have some less coverage here in this area, and some more coverage here over on the left side, and some variation here in the right part of this covered area. And this is actually the real world. And if we do later on the planning of our cellular network, then we have to keep in mind that the radiation pattern is not like a circle, but rather like a not clearly defined coil, like here in this case. And for the transmission directions, we have two different terms we have to think about. The first one is the uplink. Uplink in the area of mobile networks means the link from the mobile device to the antenna, so up to the antenna. And downlink means down from the antenna to the mobile station, to the user equipment. These are basically the terms which we use in the area of mobile networks. Now imagine that we want to cover a certain area where we know that we have some users or that we will have some users. And we now have to think about the space and think about how we place the antennas in this area to get the users connected to our network. And also we have to take into account that we obviously will have different user densities. For example, in the rural area, we will have lower densities, and in the urban areas, we have higher densities. If there are more apartments, for example, per kilometer in the urban areas and less apartments, less houses in the rural areas. And we have to cope with these different densities so that we save our resources on the one hand, and on the other hand, of course, we need to serve our users with a certain quality. And therefore, one step to cover the area, to think about how to best cover the area, is to first think about the placement of the antennas. So if we have an isotropic radiator with our ideal and omnidirectional propagation around the antenna, then we can cover the area like this, shown here on the right side. We just place it regularly in a certain distance, and then we cover the area like shown in this picture. And actually, as I said before, we don't have this isotropic radiator and like in the ideal world, but we have antennas, real antennas, which form this kind of hexagonal structure in our mobile network. That means the antenna is here in the center of such a hexagonal shape. And if we place the antennas in the same structure like these isotropic radiators, then such a hexagonal structure is formed. And this is actually our model for placing multiple antennas in an area which we have to cover as the mobile operator. But now the advantage in our ideal world is that we just need to cover the entire area with such a structure. In our real world, the disadvantage is that we have different user densities, that we have different obstacles maybe also in our real world, and this makes it a little bit more complicated to plan our network, to position the base stations, the antennas in the right way so that we can cover the area and that we can serve our mobile users also with an adequate quality. So how about the rural areas? If we go into rural areas, what is special in rural areas if we want to take into account the radio propagation? If we look into the characteristics of a mobile station and a base station, an antenna, then you see that there are 35 kilometers, which is the maximum distance between the mobile station and the antenna, the base station. And this leads to a theoretical distance between two base stations of about 70 kilometers. But actually, if we are in rural or urban or some other areas, then we should also think about the obstacles which are in between the antenna and the mobile station, and this leads to situations like this shown here. If we have a mountain in between two antennas, then we might be on the top of the mountain and we see both base stations, both antennas. But if we go further down to one of the base stations, then we see that we can only see, due to the shadowing, one of the base stations, one of the antennas. This is one phenomenon we have to pay attention to, so that we get a small overlap here on the top of the mountain and that the top is also covered, same like the other areas here around this base station. If we have a flat area, then of course we don't need to think about the shadowing. Then we more have to think about the capacity, the maximum distance, and we have to find a good compromise between other parameters. Now, a second point regarding to the division of the space could be that we think about urban areas where we have not mountains, but mostly buildings. In some cities, higher buildings, in some cities, less higher buildings. And this actually also affects our propagation characteristics when we look into the placement of our antennas. So if you look in the example here, we have the antenna on the roof of the building, and it is possible to cover a certain area here, starting from this roof, maybe also some more area if we have some flat area here on the left. But if we go here into this gap of the two buildings, then we see that there can happen some reflection, and with the reflection it is possible to receive the signals from the base station. The mobile station can receive the signals from the base station with reflections, but without reflections it is not possible actually. So we have to take into account that in urban areas there are more reflections happening. Another possibility to place a base station would be that we place it here on the ground, and therewith we can reach more users, maybe without reflections, which are here in the gap between the two buildings. But on the top of the roof it might be difficult to receive the signal, and we would need to place another base station if we look into the next gap between the next buildings in the next street, for example. So if we look into such urban areas compared to the rural areas, we see that we have much more shadowing by buildings, and also at the same time, if you look into the buildings, then you have more apartments there, you have more offices there, and therewith you need to serve significantly more users than in the rural area. In the urban area, you need to serve significantly more users than in the rural area. And this, of course, leads to lower distances, shorter distances between the antennas, because you can only serve a certain number of users in the range of one antenna. We will see that in a minute, how we can roughly calculate that. And we also have more multipath propagation, like here the reflection and the shadowing, seen from here. And this makes it more difficult to properly transmit our signal from the sender to the receiver, the uplink and in the downlink. The conclusion is that in the urban areas we will have much more base stations than in the rural areas. And we will see that if we look into the planning, then the densities of the base stations vary with the density of the population. Now, the next important aspect, if we look into the division of the resources, is the division of time. We know that we have the so-called TDMA, time division multiple access, and this enables us to serve several users when we divide the time, when we assign each user a certain time slot. And that's what we do also in the GSM network. We have a certain GSM-TDMA-frame. This is seen here on the right side. The TDMA-frame is repeated every 4.615 milliseconds. So many times in 1 second there's this frame transported, and within one frame there are 8 time slots, with each time slot 577 microseconds long. And in each of these time slots are called the bursts, and each burst has to have a certain packet structure, a certain timing structure. You see that here in this picture, and you see that the timing starts with the guard time. And the guard time is important to cope with different distances of a mobile station to the base station, to the antenna. So for example, you could have an antenna here, which is emitting the electromagnetic wave, the signal, and you could have a mobile station which is very close to the antenna, and a mobile station which is far away. Then if you look into the timing, the time which a packet takes from mobile station 1 is much shorter than the time it takes from mobile station 2. And now we can have a look at the transmission of packets in a timing diagram. So we have first the time slot which is assigned for the mobile station 1, and then the time slot for the mobile station 2. And if we say the mobile station 1 can send here within this time frame, then the mobile station 1 is also able to fulfill the timing restrictions because it's very close to the antenna. On the other hand, the mobile station 2 is farther away, and that means that the signal also travels longer from the mobile station to the antenna. And this leads actually to a certain delay. If you would sketch that in the timing diagram, it might look like this here. So the package of the mobile station 2 would actually be received later. And if you would now start again with the reception from mobile station 1, then you would get a collision here in this area where the mobile station 2 is not finished yet, but the mobile station 1 already starts with the next package. In reality, this would not be mobile station 1, but it might be another station which has this third time slot assigned, and then the collision would happen here again with mobile station 2. And now we have the guard time, which is introduced here in the GSM-TDMA-frame, and that means that if we look again in the timing diagram, we have again time slots, but we have around this times where the frames start and end, so-called guard times. And these guard times assure that if a package from a station farther away still transmits the package, then it does not collide with the next package. So, like here in this case, it is a little bit longer than the actual end, but due to the guard time here, it does not lead to a collision with the next packet. The next packet starts earlier again than this second packet, but it does not lead to a collision because of the guard time. So this is actually the meaning of the guard time here in our GSM-TDMA frame in the burst definition for our GSM transmission. And then we have a certain tail sequence at the beginning and at the end. And tail means that we have a specified sequence, a fixed defined sequence for the start and the end of such a package. And as a receiver, I would look into the air, look into the transmission and the overall transmission sequences for such a tail. And if I detect such a tail, then I know, okay, the transmission of the actual data, the data part, starts immediately after the tail. And I would detect this tail first, then the end of the tail, and the end of the tail is then the beginning of the actual payload data, the data which should be transmitted between the sender and the receiver. The data actually is divided in two parts in one of these bursts. The first part before such a training sequence and the second part after the training sequence. Data can be voice or IP-based data for electronic services. And here in the center of the data package, there's a certain training sequence. The training sequence helps us to cope with the channel characteristics. again, what does it mean if we want to somehow adapt to the channel characteristics? Imagine that we have, again, an antenna which is emitting electromagnetic waves or receiving electromagnetic waves, and that we might have a mobile station. And in this case, we have some obstacles, we have some reflection, and there are several signals received by the antenna or vice versa by the mobile station. Maybe we have a second reflector as well here. And it means actually that one signal is received here in this case 3 times by the receiver, by the antenna in this direction, in the uplink direction. And if we look into a timing diagram for these signals, then we see maybe the first signal which arrives is this one. This is a little bit lower than the original signal because of the shadowing. Then we have a signal which might be a little bit stronger, but later arriving. And again, the third reflection, the third signal, is received also with the same energy, but again a little bit lower. And this would be the signal which is received at the receiver. And the receiver now has the difficult task to make one symbol out of this received signal. And the receiver might not know what actually was sent, but with the help of a training sequence, a defined training sequence, the mobile station in this case would send this training sequence, and it would lead to such a characteristic reception like shown here in this timing diagram. And the receiver would then know that there are some obstacles in the way from the mobile station to the base station. And this is then further taken to process the received data and to take into account this propagation characteristics here, so that at the end, with the knowledge of the training sequence, we can make the correct signal out of this received signal. So basically that's all what happens in one burst, and each user in a cell, each user which is assigned to an antenna is allowed to use one of these bursts. It repeats so that the user, for example, gets the 6th burst, and every 8 time slots the user is allowed to transmit the next bit of data, the next chunk of the data it wants to transmit. That means, for example, that during a call from a mobile station into the network, the mobile station might get the 6th time slot, the 6th burst assigned, and then it repeats using the 6th time slot during the entire duration of the call. Beside the ability to switch calls within our network, we also want to enable data transmission. Data transmission, for example, for internet services, for internet connection, and therefore the GPRS was developed, the General Packet Radio Service. And General Packet Radio Service is a principle on top of the GSM-TDMA-frame, and basically it means that bursts are aggregated to transmit data. In the downlink, this aggregation is just done spontaneously because the base station and the base station controller have control of the time slots anyway, of the bursts anyway, so they just use the bursts which are required. In the uplink, the mobile station first has to request that there's a transmission pending, and if the base station controller allows the transmission, then the mobile station transmits in aggregated bursts the data the request, for example, the request for an internet page. And this is basically the GPRS, which works on top of the GSM system. Later on, there were made extensions like Edge, for example, and in Edge, there's also some change in encoding, but in GPRS, we have only this aggregation of the bursts so that we can increase the data rate. Additionally to this radio subsystem principle for GPRS, we also have to add some switching in the core network, and that means that after the base station controller, the data is split from the voice call, and the data is transmitted then into a data network so that the internet connection can be set up and all the required data are transferred from and to the mobile station. So this was a view on the radio subsystem, on some main parts of the radio subsystem, and we have seen that we need antennas. We need to place them properly to cover an area, and we have the TDMA here in our GSM network to assign a certain time for transmission of the data to each user.